Properties of acids. So we're looking at acids and base, and I'm just going to go a little bit over the properties of acids first and properties of bases. So acids have a pH of less than 7. Some of this just might be review. They taste sour. Don't go around tasting things and saying, well, it's sour, it's acid. You never just want to taste random things, but in general, they taste sour. They conduct electricity. Some are strong, some are weak electrolytes. That means they conduct electricity. A charge goes through them. They react with metals to form hydrogen gas, H2. They change indicators, like litmus paper red. So blue to red, acid. They react with hydroxides, OHs, to form water and salt. So that means there might be some other hydroxide, like an XOH or a YOH, something with a hydroxide in it. So examples of acids are like the juices. They're sour. Properties of bases. pH is greater than 7. They react with acids to form water and salts. They taste bitter, but again, don't go around tasting things to see if they're sour or bitter, to see if they're acidic or basic. And they feel slippery. And don't go around dumping liquids on the floor to see if you slip on them. So examples of some bases are cleaning fluids. Most cleaning fluids are bases. They can be strong or weak electrolytes. That means they conduct electricity just like acids. And the reason why acids and bases conduct electricity is because the dissociation, and they leave charges when they dissociate. Bases, negative. They change indicators. Litmus goes to blue, so red will go to blue. There are types of acids and bases. There's different types. And there's several definitions of what an acid and what a base are. So let's look at them. And they're all correct. Okay, so Arrhenius acid. Arrhenius acids produce hydrogen ions in aqueous solutions. Now, hydrogen ions are also symbolized by H+, and they are called protons. They are exactly the same thing. Protons, H+, hydrogen ions in an aqueous solution. So example here, we have hydrogen chloride as the gas. It will dissociate into hydrogen ions and chlorine ions, and you can see the charges there. That's why we can conduct it can conduct electricity. Now, as we said before, hydrogen chloride, because it's the gas, but once it's an acid, once it's in water or an aqueous solution, it's an acid, a hydrochloric acid, because now we have these free protons there able to do damage. So example here of another dissociation, we have sulfuric acid here in water, and we make a hydronium ion, because in water, the hydrogen ion goes to the water, and now we have H3O+, and we have the hydrogen sulfate ion. So one of these hydrogens left, and it gave it to water. Here's some common acids that you've probably seen. Hydrochloric acid, that's the type of acid that's in your stomach. Nitric acid, sulfuric acid, battery acid, phosphoric acid, ethanoic acid, and carbonic acid. Now, if you look at all of these, one way that you can tell something's an acid is by this leading hydrogen, because these are the ones that dissociate. And ethanoic acid doesn't have a leading hydrogen, but it has this hydrogen, and we'll talk about that later. So a polyprotic acid. Poly means many. So it's important to know that it's the hydrogen that makes it an acid. And when that hydrogen is ionized, that's what gives the acid its properties. That's what makes it an acid. And some have more than one ionizable, which means more than one hydrogen ion that leaves and goes into solution. So for example, nitric acid is a monoprotic. It only has one hydrogen that goes into solution. Sulfuric acid is diprotic. Di, like means two. like you ride a bicycle to school. So they have two hydrogen ions. Phosphoric acid is triprotic. They will have three hydrogen ions that are ionized. Now, what's an Arrhenius base? It's a base that produces hydroxide ions when dissolved in water. So a hydroxide ion is OH minus. So for example here, this is sodium hydroxide, and when it dissociates, it's a solid, but when it's in water, it will dissociate into a sodium ion and a hydroxide. Only one kind of base. Now, NH3 ammonia could not be Arrhenius base. This is a base, but it's not Arrhenius base because Arrhenius bases are defined only by those that produce hydroxide ions. So it's easy to see what Arrhenius base is. If they have an OH in it, that's a base, Arrhenius base. But there are other types of bases if you look at the different types of definition of a base. Here are some common bases. The first one, potassium hydroxide, has the OH, sodium hydroxide, OH, calcium hydroxide, OH, and magnesium hydroxide, OH. And is it soluble in water? Will it dissolve well in water? Well, the first two are very soluble. They dissolve very well in water. And the other two, not so much. So these, since they're OH, they're Arrhenius bases. That's classic definition. There's another definition of acids and bases. That's the Bronsted-Lowry definition. That is saying an acid is a proton donor or hydrogen ion donor. Same thing. Okay, so again, everything's about the hydrogen ion with acids. And a base is a proton acceptor. It accepts the proton. Base will take a proton, and acid will give a proton. Acids and bases with Bronsted-Lowry always come in pairs because you can't have a giver without a taker. You can't take something without having someone give it to you. HCl is an acid. When it dissolves in water, it gives its proton to water, the H plus to water. Example here, and I guess that's what this arrow is doing down here. I get kind of messed up here, so we should have a double arrow here. The HCl, hydrogen chloride, in water will then give its proton to water, and now we have H3O plus Cl. The hydronium ion, hydronium, plus the chlorine. The water is a base. This is the base. It takes the proton. The proton acceptor. It accepts the proton and it makes hydronium ion now. So the Bronsted-Lowry, again, come in pairs. So the general equation is you have a acid, which is denoted by the H plus water. You get hydronium, and you'll get a acid with the or the A that has a negative charge. So this A could be any sort of element, just as long as it has that proton to donate. So what that is the acid and the base. In this case, the base is water. As long as it accepts a proton, it's a base. Doesn't matter really what it is. If it accepts a proton, it'll be a base under Bronsted-Lowry. So the acid becomes the conjugate acid because it lost it. And the base, so this is the acid, and this is the base. The acid gave the proton, and the base takes the proton. And the thing that takes the proton is now, after it takes the proton, is a conjugate acid. And the acid, after it gave the proton away, is the conjugate base. So the acid becomes the base becomes the acid. Because in equilibrium, remember, it can go back the other way. So this now can give the proton back to the acid, or I should say give it back to the base. So it goes flip-flop. The acid now becomes a conjugate base. The base can become the conjugate acid, and the conjugate acid can go back to the base, and the conjugate base goes back to the acid. And it's in equilibrium. Okay, back and forth, back and forth. Now in this case, we have a base plus water goes to BH plus OH minus. Water is the acid because it's going to donate the proton. This base will take the proton, and we can see that the base took the proton and the acid water got rid of the proton. So the base and the base goes now to the conjugate acid, and the acid is now the conjugate base. So water can be a base or an acid. Let's look at this example. In this case, here's the acid. Ammonia here is the base because it will take an acid from the water. Because the ammonium ion is now the acid, the conjugate acid. Water loses the proton because it's an acid and now becomes a conjugate base. So it goes back and forth, back and forth. The base becomes a conjugate acid, the acid becomes a conjugate base, and they switch. Lewis acids and bases have another definition. The acids in a Lewis acid will accept a pair of protons. The bases will donate a pair. So let's look at this case. Here we have an acid, and this would be the base. If we put them together, the proton or the hydrogen ion will accept those pairs of electrons. They just meet together, and we have water. So the acids will accept a pair. So a way to remember it, acids will accept electrons. Bases donate electrons. But they really, the way I remember it is the acids, acids accept to AA. Another example of a Lewis acid and Lewis base, we have H and NH3, and the H will be the acid, so it will accept the electron pair. NH3 will be the base, and it donates the electron pair in this covalent bond here. So we have the acid and base at that point here, acid and base. And what about this next case? We have the BF3 plus the fluorine atom, or ion, and that will go. We have the boron trifluoride is the acid, the fluorine ion is the base, then we get boron tetrafluoride as the final product. So these are Lewis acids and bases, electron accepting, base donating. Here I have a nice acid-base definition table. Types here, what the definition of an acid is, and what the definition of the base is. We have the three, Arrhenius, Bronsted, Lowry, and Lewis. And notice the big definition of the acids are proton donor and producer. It's really the same thing. For Arrhenius, the OH it produces OH, hydroxide, and Bronsted Lowry accepts protons, and Lewis all about the electrons.